welcome everyone. Today I want to talk about the Taylor series, which if you haven't been here already, I have a website called mathsheets.com with a Z, and I just uploaded this math sheets there, so you can check it out and read it yourself. But we're going to kind of go through it and talk about the Taylor series. So a couple days ago, I went to the physics library to study late at night, and there was some stuff on the whiteboard about the Taylor series. Somebody was solving a problem finding the Taylor series. And so I told my friend, I was like, I challenge you, prove the Taylor series right now. And I didn't think it would be too hard. He didn't think it would be too hard. Neither of us could do it. Neither of us that night could figure out how to prove the Taylor series. And it was extremely frustrating to me because here I am looking up to Richard P. Feynman, who preaches that we should never just rely on a formula. We should always understand the physics of what's happening, the machinery of the math that we're using. And here I am, a physics major, using the Taylor series. On the order of like 10 to the 3, probably thousands of times during the course of 5 to 6 years or longer. And never once did I figure out where it comes from. And the proofs that I had seen, or the proofs that I looked up and researched, they all started from assuming the Taylor series had a very specific form, and then using some sort of algebraic argument or some sort of induction argument, and the perfect algebraic trick, maybe the best proof that I saw, iterated the mean value theorem, essentially, and proved that the Taylor series formula works. And there's nothing wrong with that, but for me, it's a little bit frustrating because if I was Taylor and I didn't have a formula, right, at my disposal, how would I come up with that proof? If I'm starting my proof with the form of the Taylor series formula, there's no way that that's going to be an original proof. Like, I'm inherently going to be biased by the fact that I know the answer. I know what the answer should look like. Right? And even myself, when I thought about this for the past couple days and came up with my own explanation of the Taylor series, even I was biased by thinking and knowing what I needed to get to, right? So that's just something to keep in mind. But I just wanted to give my take on the Taylor series, where I think it comes from. So essentially, we start with a few pieces of information. We start with the function f, okay? And for these graphic examples, I'm going to draw the function in red. Okay, so I'm going to use the example that everyone uses, e to the x, okay? But anyways, we're starting with some function. Now keep in mind that the graph of this function, ironically enough, is actually graphed using Taylor series. So the fact that I can graph a Taylor series and it matches the function arbitrarily well is also a biased fact, because every graphing software that I know of is using the Taylor series to graph this. But that's fine. So anyways, the point is that this is math. We don't need to rely on a graph, right? So what do we know? We know we have a function f. We know that it has n plus 1 derivatives. We know the value of the function and the value of those derivatives at a point, x naught, let's say. And we know that the nth plus 1 derivative is bounded. Okay? So I'm going to assume that the nth plus 1 derivative is continuous on a closed interval ab, and that it's bounded between a constant, negative m and n. Okay? And this constant is shown here in green. So I've taken e to the x, its derivative is itself, so it's never going to change from picture to picture, which is a little bit confusing. But as I move from picture to picture, I'm really going to be taking the antiderivative, or the integral of the previous picture. So just keep that in mind. It's just with this nice example, e to the x, its integral or its derivative, it's invariant, basically, up to a constant. So it works for a nice example, but maybe it's a bit too special of a case. Maybe it's a little bit confusing because really from each figure, we're actually going to be taking the antiderivative, as you'll see. Okay, So I start with a bound on the nth plus 1 derivative. And from here, I'm basically going to do the worst possible approximation of the nth plus 1 derivative. Namely, I know its value at the point 0. I know that it's 1 at 0. And so what I'm going to do is I'm going to approximate it to just be, let's just say it's the constant function 1. It's a pretty bad guess, right? But this black line here is my initial guess, okay? And it's called a 0th order approximation. Now this is my guess for the value of the nth derivative. Yeah, for the nth derivative, just to make sure I'm doing things right. So yeah, so the nth derivative I'm going to guess is, let's just say its value at x naught. So I'm guessing it's a constant. And my guess, my 0th order approximation, has some error associated to it, and I want to bound that error. And the way that I'm going to bound the error of the 0th order approximation is essentially I start with a bound on the nth plus 1 derivative, and then I integrate that bound. And that basically starts with this picture here, starts at the point that I know, and then I'm going to take the cumulative area function of these 3 curves, the 2 green curves and the red curve, the cumulative area function, starting at 0 and moving to the right, okay? Or in this, starting at x naught, moving to the right, okay? And the point that here is that the cumulative area of e to the x, the cumulative area function of e to the x, looks like itself. So we're kind of deceiving you here, but when I pass to the cumulative area function of e to the x, I get back itself, okay? Now when I pass to the cumulative area function of these error bars are flat lines, therefore the cumulative area function underneath them grows linearly, and it's a line with slope given by the height of this bound. So I produce a cone by integrating the bounds that I know. I produce a cone which bounds my error in my first order approximation. Okay, so I have this first approximation given by taking the cumulative area, or the integral, starting at the point that I know and moving forward. Okay, and so I can bound the nth derivative between not just a constant, but inside of a cone. And so you have this inequality, and this is a first order Taylor approximation of the nth derivative. Okay, well I can do better. I can do the same thing. Now I have this picture. Now I'm going to integrate it again. I'm going to take the cumulative area. Okay. Now, importantly speaking, I'm going to take the cumulative area of this red line and the cumulative area of the error bars. Okay. And I'm also going to take the cumulative area of my first guess, the black line. Okay. Now what happens here? Okay. Well, basically, go ahead and integrate this inequality, and what you're going to get is the following expression. So when the cone, you take the cumulative area of the cone, or basically of a line, the cumulative area function of a line is basically a growing triangle. Okay, so that's going to have area. That's the cumulative area function will look like a quadratic, x squared over 2. Okay. And so that's going to be my error bounds, is going to be this quadratic cone. And then the inside of this sandwich here, when it gets integrated, I get that the nth plus 1 derivative of x, of f evaluated at x. So I get these two terms from fn of x, the function that I'm trying to approximate. This term I know the information about. This is basically comes from the fundamental theorem of calculus, which says that, the integral undoes the derivative. The act of looking at the cumulative area of a function undoes the act of looking at its instantaneous rate of change. Or in other words, if I look at the instantaneous rate of change of a cumulative area function, I get the height of the graph which I'm taking the cumulative area of. Okay? So we're using the fundamental theorem of calculus here. Okay, so this guy is the integral of fn of x in the previous inequality. And then when I integrate fn of x naught, which is just a constant number that I know, that's integrating this black line here, I get fn of x naught times x minus x naught, which is, again, a line of slope given by guess what? The slope that I know the information about. Okay. So it's not Sherlock Holmes here. Sherlock Holmes didn't come and figure out the Taylor series formula. It comes from the integral. You're integrating your best guess, which is a constant, and you integrate that best guess and use the information that you know to get a new guess that's a line. And the line is the cumulative area of a constant. And that line has slope exactly given by the slope of the derivative, which you know. You know that the only information that you know, that the slope at this point 1. Okay, so the slope of the function at this point 1 is exactly the slope of my line that I'm approximating. And what is this additional green cone here? This cone is the error cone that we've now integrated. Okay, so moving, it's not exactly the error cone for visual purposes because the error cone is just going to look like a literal quadratic cone, but that error cone is bounding the difference between our approximation and the function. Okay, so for visual purposes, I went ahead and graphed the error cone, added like the error, the approximate, as I say here, the approximation plus or minus the error bound. Okay, so I basically am starting at this black line and then adding the error cone onto this black line, which is exactly the visual picture that we want, which is that how sure am I that this line here is actually a good guess? And it's a pretty good guess in this region, right? Like this cone is almost sandwiching my approximation and the true function, but the further I go out, notice the cone is diverging, right? And I'm losing information. Now notice that the red line, I see the red line here, and I'm talking to you, and we can both see the red line. But in the real world, you can't see the red line. The red line is invisible, okay? So you only know your approximation, but you also know the cone. And this green cone is telling you, okay, how good is my approximation? Well, it looks pretty good if I'm like really close to 1 there, okay? But notice, we've only gone one step. We've only done the first order Taylor approximation. This black line is literally the first order Taylor approximation for the n-1 derivative, okay? All right, so I'm going to do what I just did again. Now I'm going to integrate everything, basically everything in this picture, okay? I'm going to take the cumulative area of everything in this picture. And the constant of integration, guess what? The constant of integration is the extra piece of information that I know. Namely, I know more information that I'm using here. I know the values of the previous n-2 derivative at x naught. I know the value of the n-2 derivative at x naught. I haven't used that information yet. The way that I use that information is via integration. Looking at the cumulative area function, the constant of integration, each time I integrate, the constant of integration allows me to utilize more information that I know. Okay? Now, if I integrate these error bounds, what happens geometrically is I'm looking at the cumulative area of a growing triangle. So geometrically, if you visualize a triangle that's expanding in three-dimensional space, what do you get? You get a tetrahedron, okay? So notice this tetrahedron is the cumulative volume, right? The cumulative area, the cumulative integral, whatever, of a triangle. So I start with this tiny triangle here, maybe in this corner here, and then you can picture moving the triangle and expanding the triangle out until I get all the way to this base of the tetrahedron. Okay, so if you can think about this, the tetrahedron is the cumulative area function of the triangle. So what do you know? If you integrate the x squared over 2, if you integrate x squared over 2, you get x cubed over 3, the volume of this tetrahedron. You're passing to the cumulative area of the previous function. So if I started with a line and then I looked at the cumulative area function of the line, it's a growing triangle. Now if I look at the cumulative volume of that growing triangle, the cumulative area function of that growing triangle, I get a tetrahedron. And this process will be continued. This is the geometric realization of the error, of integrating the error term, okay? And so I'm going to get some higher order polynomial, in this case x cubed over 3 factorial. If I integrate it again, I'm going to get the volume of a 4-dimensional tetrahedron, and it's going to be x to the 4th over 4 factorial, and so on and so forth. And the point that I want to emphasize here is that because of this factor 1/6 or 1 over n factorial, for a fixed x, this volume is going to 0, okay? As I send the dimension, as I keep integrating, as I send the dimension of my space out to infinity, okay? So maybe I'll comment on this a little bit more later. I don't want to get too sidetracked here. Let's keep going with our discussion. So we have this first order approximation. We're going to integrate everything, take the cumulative area function of everything in this diagram. I briefly explained that when I take the cumulative area of this green quadratic error cone, I'm going to get a cubic error cone. And it'll look something like this. Oh, that looks nice. Okay, so you can see now the cone, the error cone, is really collapsing down. Really collapsing down on the function. So it's basically telling me my approximation is really, really good in this region, right? Obviously depends on the context, depends on the industry that you're working in. This might be not even close to enough precision, depending on what you're doing. But the point is that the approximation is getting noticeably, like very, very, noticeably better. And mathematically, it's getting better by orders of magnitude. So that's very powerful. And basically, again, we have this black line here, which is a quadratic function. Now this black line is now the second order Taylor approximation. Okay, so this black line is the second order Taylor approximation of the nth minus 2 derivative, right? We've integrated, and now we're approximating the n minus 2 derivative by the second order Taylor expansion, and we've bounded it in this cubic error cone. Okay. All right, and you can just keep repeating this process. You can keep integrating this inequality here, and you're going to get, your error cone is going to collapse down, basically because of the fact that this error cone for a fixed point x, if I fix the side length x minus x naught, then this error for is exactly the volume of a tetrahedron in n-dimensional space, and that volume is going to go to 0 as n goes to infinity. In fact, it's going to go to 0 very, very quickly because of how quickly n factorial grows. N factorial dominates any exponential growth, right? N factorial dominates the growth of this numerator here. Okay, and so what does that tell me? Well, that's basically, how do I go deeper into this understanding? Well, the reason why this volume is going to 0 is I send space out to infinity, right? Why is the volume going to 0? Well, that just has to do with flat space. We're basically at the bare bones of the axioms at this point, right? The notion of the volume of this tetrahedron is deeply tied to the geometry of flat space. And it just so happens that if I use flat space, just like we always are taught to use and never question, if my space is flat, then just so happens that these tetrahedrons in higher and higher dimensions, their volume decays really quickly. So that allows me, upon integration of the cumulative error, that allows me to basically get this error cone to collapse in on itself. And what does that look like when the error cone collapses? Looks something like this. Okay, so this is a visual representation of each error cone. As I integrate each error cone, you can see as I move down the rainbow here, from red as a first order approximation, first order cone of slope 1 with the Taylor series. Now if I integrate that cone, I get a quadratic cone. So this is the error cone of order 2. Now the green cone is error cone of order 3, and so forth. Blue is order 4, purple is order 5, and black is order 6. Ran out of color, so I couldn't do any more. But you can kind of see how the error cones are collapsing. Okay? Which is telling us that the Taylor series is getting better and better at approximating the function in this region. Look at this black error cone. Look at how good of an approximation we have in the interval, let's say -1 to 1, right? And -1 to 1 is a pretty big interval. I mean, it's all relative, right? But the point is, like, this is a powerful approximation. These cones are collapsing in a way that, is kind of profound and unprecedented. And it's the fact that these cones are collapsing each time we take the cumulative area function. It's a product of the fundamental theorem of calculus, but I mean, it's just a geometric fact. And if you think about, if I look at the cumulative area, if I start with this really, really bad approximation here, okay? If I start with a really, really bad approximation, let's say a zeroth order approximation, and now I start taking the cumulative area function, notice that the relative error of the cumulative error, okay, the cumulative area function, I wish I had a freaking pen. So the cumulative area function underneath the black curve here, okay, let's go over 2 units. Hopefully you can see my mouse. If I go over 2 units on the x-axis, then I have a cumulative area of this rectangle here underneath the black line. And the cumulative area underneath the true function, the red line, is pretty close to the cumulative area. The only difference is this little triangle here. Okay? But the cumulative area, if I go over 2 units to the right of the black line, my zeroth order approximation, and the true value of the function, the cumulative areas are kind of close, right? The error and the difference between the cumulative areas is only this small triangle here. So we can see that the relative error of the cumulative area is less. So that's another kind of intuitive reason of why integrating to the cumulative area function gives you a better and better approximation. It gives you relatively less and less error. But notice that we're not just using integration to gain more information. We're using integration alongside the knowledge of the integration constant, which is, of course, the value of the, derivative, whatever derivative of the function that we know. Let's say we've integrated at this point where we integrate this inequality again. Now we know the value, as I emphasized before, we know the value of the nth minus 2 derivative. So we have additional information that the integral is kind of extracting for us. And since we have that additional information, we can use the cumulative area function and obtain a more robust approximation, an approximation with less relative error at each step of this process. Okay? So this is how I think that I would come up with the Taylor series, right? Like, I would start with the bare bones of what I know, which is the bound between the nth plus 1 derivative. The bound of the nth plus 1 derivative is bounded between negative m and m. I would start there and just start integrating. I'm not sure if that's how Taylor did it, but this is important to me because the Taylor series is something that I use on a daily basis, and I'm sure a lot of you use it. And it's important to me that we see the meaning, we see the reasons, we see the intuition, the geometric intuition behind this formula, rather than just using the formula over and over and never understanding where it came from. And even our proofs, even our most rigorous classes, maybe even in analysis, if you've taken that far, maybe you learned the Taylor series in calculus, that's fine. It doesn't matter if you've taken a bunch of years of advanced math. Even in the advanced math courses, sometimes the proofs are really just archaic, are really just kind of symbolic, and they're just using the definitions and using the right algebraic tricks, and everything works, but they don't really explain how to come up with this proof, the intuition, right? You don't have a formula to begin with. You need to figure out how to come up with this polynomial approximation without assuming that it exists to begin with. Now, of course, you could start with an infinite series and start differentiating it and then equate the coefficients. That's what most people do. And there's nothing wrong with that. That's a valid approach, okay? But I hope that this offered you a different perspective. And thank you for your time. And if you've